Finally, we've made it to the last video. This is kind of the point of everything that we've been building towards all week. Vector addition is really what I've been slowly trying to build towards. So here's the thing, is we use vectors to represent voltages, AC voltages. So what do we get when we take a couple of voltages and we add them together? Okay, two power supplies, hook them up together, what do we get as a result, for example? Okay, or maybe two currents, okay, come together in a node and off they go, sort of thing. Okay, we can imagine a number of different scenarios where this might come into play. We will certainly discover there are many of them, but let's just jump right into this and figure it out. Okay, so vector addition. How do we add two vectors together? If we have two separate vectors representing two voltages or two currents, and we want to add them together, how do we do that? So I have, let's call this vector A, which represents 5 volts. And then I have vector B, which represents 7 volts. Well, how do we add them together? Well, the trick is this. This is the rule always. Place them tip to tail. Okay, so we're going to show vector A. We're going to place vector B tip to tail so that it's right there. So we have A plus B. And I'm going to use red to show my resultant vector. Okay, so R, the resultant vector, equals 5 plus 7, 12 volts. How easy is that? Okay? Well, it's a pretty good start, but we're not quite done yet. This represents these vectors represent voltages, right? An AC sine wave. Okay? These two vectors are in exactly the same direction to represent two sine waves that are in phase. Okay? So if I move back from the vector and I actually show the sine wave that these vectors represent, there's sine wave A, which represents a voltage of 5 volts. And here's vector B, which is a voltage of 7 volts. An AC sine wave, AC voltage, 7 volts. Okay? So no problem. Add them up. Okay? But what if vector B oh dear. I tried to actually make that to scale. What if that was vector B? Or what if that was voltage B? Okay, now vector B is going to be drawn like that. Okay, these two voltages are out of phase by 180 degrees. And so vector B has to be drawn in exactly the opposite direction. Well, how do we add them up? No problem. Place them tip to tail. So there's vector B, and there's our resultant vector, minus 2 volts. Okay, or 2 volts at 180 degrees, or however you want to decide to recognize that we have subtracted a larger value from a smaller value. Okay, there's ways to go about that. That's not really what we want to focus on. Okay, because those are the easy options. In these two cases, we have voltages that are either in phase or exactly 180 degrees out of phase. Okay, and we're working exclusively on the x-axis. Okay, here's where things get complicated. Let's try this again. let's leave A exactly where it was. Okay, that was the same voltage A and vector A we had before. So let's draw vector A equals 5 volts. Okay, now let's draw vector B. I'm going to change my value here. It's just going to be tinier. Let's say that's B, and it's 3 volts. Well, I tried to draw this so that it looks like it's maybe about 60 or 70 degrees from there to there. Maybe that's 70 degrees. And so from there to there is that same 70 degrees. So we have a phase shift now of 70 degrees, which means vector B equals 3 volts. Maybe I'm going to make that a little bit shorter. There's vector B. How do we add those two together? Well, we place them tip to tail. Let's slide that over. Let's take vector B. Let's slide it right into place. There it is. B equals 3 volts. Our resultant vector, there's R. R equals big old question mark. That is what we need to figure out. Okay? And 5 plus 3 is 8. Is that 8? No, absolutely is not. It's something less than 8, right? Because we haven't followed the 3 and the 5. We've cut the corner off. So this is the challenge ahead of us. Okay? And the thing is that we can't just add these up because they're not in the same direction. Okay? We've got to do some work to figure this out. Okay? So how do we do this? Well, this is the reason for the previous video that introduced the Cartesian coordinate system. Okay? Because what we have here, when we talk about these vectors, okay, we are still using the polar coordinate system, right? We're talking about a magnitude and a direction. Okay, we're talking about how long is the vector and what is the direction of the vector. And we end up with things that do not align, and so we can't add them up. Okay? What we need to do is we need to translate these polar coordinates to the Cartesian coordinate system, which gives us x and y values. We've got vertical values, we've got horizontal values, we have numbers that line up that we can actually just add up. Okay, so that is the task ahead of us. So, so here's our polar coordinate system. Let's see, A was blue. So right here we have A equals, and it is 5 volts at an angle of 0 degrees. Okay? And then we had B nope, it was only 3, wasn't it? And that's, so B equals 3 volts at an angle of, I'm going to say minus 70 degrees. Okay, minus 70 is also 290, right? So it's 360 minus 70 degrees would be 290 degrees. So just like we talked about the leading and lagging, okay, where we've got a whole bunch of different ways we can express the relationship between two vectors. Here we always have two different options in terms of how we want to express the direction of that vector on the polar coordinate system. Now let's move on over to the rectangular. Notice I used the terms rectangular coordinate system and Cartesian coordinate system interchangeably. I do that on purpose just so you're familiar with both. Okay, so what we're going to do here is we are not going to draw a vector. Okay, we are going to plot a point which represents the tip of the vector right here. Okay? And this first one's easy because it's right on the x-axis. Okay? So how far out the x-axis does it go? 5 volts. And does it go up or down vertically on the y-axis? No, it doesn't. So I can identify this point easy enough. Right here, this is 5, 0. So that point on the rectangular coordinate system represents the tip of this first vector, vector A. Now, we have to find this point down here, which is B. It's going to have an x value, and it's going to have a y value. Okay, how do we find this? There's a question. How do we solve? What's the answer? Right angle triangle. Okay, so watch what we're going to do here. We come back to this vector. Okay, if we fill this in right here, grab a different color. Right there is our right angle triangle. Okay, the vector, which is 3 volts, is our hypotenuse. Okay, this is our angle of interest right here, okay, which is the minus 70. Okay, and so across from the angle of interest over here is our y coordinate, and it is the opposite of our right angle triangle. And up here, okay, this line here, which finishes the triangle, makes up part of the angle of interest, which makes it the adjacent. And it's going to tell us how far this point stretches out from the origin on the x-axis. So the x-axis is the adjacent of our right angle triangle. Okay, so this is the reason we had to spend time learning about SOHCAHTOA, because this right angle triangle tells us how to find these two coordinates right here. Okay, the x and the y axis over here in the rectangular coordinate system represent the opposite and the adjacent of the right angle triangle, while the vector, the magnitude of the vector expressed in the polar coordinate system, is the hypotenuse. Okay, so what I like to do when we get into this math is I always like to find a spot to do this. Start right there, SOHCAHTOA. Okay, I always go back. I don't shortcut anything. I start at the beginning every single time. Okay, let's say I want to find the x value. Let's start with the x. So the x is the adjacent. So I know the angle, and I know the hypotenuse, and I'm trying to find the adjacent. So am I going to use sine, cos, or tan? This is the thought process every single time. Well, if I want to use sine, I need to know the hypotenuse to find the opposite. Well, I'm not trying to find the opposite, so let's move on. Here I can use cos to use the hypotenuse to find the adjacent. So those are the variables that I'm looking for. So to find the value of x, my equation is going to be the cos of the angle theta is equal to the adjacent over the hypotenuse. Okay, there's my equation. Okay, I know the angle, I know the hypotenuse, I'm trying to find the adjacent. Okay, so a little bit of algebra there. I need to isolate the a, so it's going to be a equals, the h is going to come across the equal sign and go up and join what's already there in the numerator, so it's going to be the cos of the angle theta times h. Okay, so now let's flip this around. So the statement is a equals, what is a equal? The cos of negative 70 degrees. The cos of minus 70. Now you could drop the minus sign here, okay, and your calculator would perform the work for you. You just have to make sure you add it back in again at the end. Okay, so this is the really important part. Grab your calculator and let's give this a try. So I'm just going to plug in 70 and ask for the cos. Oh, I have to do cos 70. And it tells me that it's 0.342. Okay, that's the cos of 70 degrees. What if I do the cos of 70 and add a negative sign there equals, well, it doesn't like that either, cos negative 70 equals 0.342. So look at that. It ignored the negative sign. Now, why did it ignore the negative sign? Or at least it didn't make a difference. How come? Well, what are we trying to find? We're trying to find the value for x. We know that we're going to land down here in quadrant 4, and in quadrant 4 we have a positive value for x. So it turns out whether we include that negative sign or whether we don't, we still end up with a positive answer for the cos of that angle. Okay? It's not always going to happen, which is why it's so important to go through this thought process to decide if you're on the right track. Okay? Especially when you get into tan, because of that freaky tan graph that we looked at. Sometimes you just, like here we can force the calculator to tell us the right thing by telling it there's a negative sign here. Within the tan function, you can't even accomplish that. Okay, so watch out for that when you get there. You'll see what I mean when it happens to you. Okay, so cos of minus 70 times the hypotenuse, which is 3, equals. Okay, so we decided the cos of 70 degrees, or the cos of negative 70 degrees, is 0.342. Multiply that by 3, and we get an answer of 1.0, let's round that to 1.03. 1.03. Okay, so 1.03, I think I want to use black for this. Try to be consistent. We're doing vector b here. 1.03. Okay, so that's our x value. What about our y value? Okay, so our y value is the opposite of our triangle. So we've now calculated our adjacent. So we could use tan. Use the adjacent to find the opposite. My recommendation is to avoid drifting of rounding error. Try to avoid using calculated numbers. Sometimes you're forced into it. You don't have any choice. But when you're given a choice, and we have many choices to go in particular directions, when you get the choice, I would suggest avoid using calculated numbers when you have the option of going back and using numbers that are given. So we were given the angle. Okay, I had estimated initially, but we're running with it. We were given the hypotenuse, so we're trying to find the opposite. Let's use sine. Okay, so one more time, the equation is, like I said, start at the very beginning, never skip any steps. Start at the beginning. What is the equation? The sine of the angle theta is equal to opposite over hypotenuse. Opposite over hypotenuse. We're trying to solve for the opposite, so the O is going to remain there. Hypotenuse is going to come across and up. Sine of the angle theta times the hypotenuse. Let's flip the whole thing around so we can work with the mathematical equation that says the opposite is equal to the sine of the angle. So it's the sine of the angle negative 70. Let's go through this process again. Let's ignore the negative sign for a second. What is the sine of 70 degrees? It is 0.9396. Okay? What happens when we include the negative sign? Now the reason I'm doing this, because remember, a negative angle inside a right angle triangle is nonsensical. So if you need to work with an actual right angle triangle, then that negative sign doesn't make any sense to us, so we have to ignore it. So I ignored it, and we got a positive answer, of course. But if we get the sine of negative 70 degrees equals, now we're given a number, it's the same absolute number, 0.9396, etc., but it is now a negative value. Okay? Well, why is that? Well, look at where we're landing, right? The end of this vector is here in quadrant 4, And we know that in quadrant 4, we're going to have a positive x value and a negative y value. So it makes sense that we've got a negative number right now. Okay, so it's negative 9396, etc. Okay, without eliminating that number from my calculator, I'm looking at this long string of decimal points. Okay, so this will minimize our rounding error. I'm going to take that and multiply it by the hypotenuse, which is 3, which gives me an answer of negative 2.82. Now I'm going to round that a little bit. Equals, this is times h out here, and this is negative 2.82. Way out here, negative 2.82. This black marker doesn't work so well. Let me try another one. A little better, maybe. Okay, so there we go. We have now plotted vector B on our Cartesian coordinate system. Okay, what is the advantage of that? What does that do for us? Now, we can do the vector addition. The whole point of this process, we can add that together because we are not adding vectors that are pointing in different directions. What we can add are the x coordinates and the y coordinates, and we end up with our new coordinate. Okay, so for example, the x values, we have 5 and we have 1.03. So they're going to add together, okay, give us 6.03. And then the y is going to be 0 minus 2.82. So we're going to end up right there. Okay, and that is, so 6.03 by minus 2.82. So there it is. Okay, I'm afraid I'm not quite to scale here, but that's okay. 70 degrees is probably going to put us back here as opposed to right there. We've pushed this out a little bit, but we've got the right numbers. 2.82. It's hard to read, sorry. Okay, we're not quite done. Okay, because that is now the location of the point expressed on the rectangular coordinate system. But everything we've done up until this point has been done in the polar coordinate system. And so ultimately that's what we want to end up with. The question is, when we add these two vectors together, what does the resultant vector look like? And the answer is, it's going to sit right about there. There is the resultant vector. So now we want to find out the direction and magnitude of that vector. Okay, so once again, we need a right angle triangle. I need to make myself some room. There's that right angle triangle. We want to know its direction. We don't know that angle yet. Okay, the angle theta is one of the things we have to find. Okay, we also don't know the hypotenuse. All right, but we do know, so this is the angle that makes this the adjacent. We know what that is, and this is the opposite, and we know what that is. Okay, so how far from the origin on the horizontal plane is the x value, and that is the adjacent, and so that is 6.03. And how far below the origin we are on the vertical plane is the y-axis, and that's negative 2.82. Negative 2.82. Again, the notion that a side of a triangle has a negative value doesn't make sense. Okay, so we could drop that negative and we could pick it up at the end, just as long as we know what it tells us. Okay, so for example, the first thing I think we want to do is use Pythagoras to find the size of the third side, the length of the third side. So Pythagoras says that the hypotenuse equals the square root of the opposite squared plus the adjacent squared. Okay, equals remember, don't forget to include that, equals the square root of the opposite, which is negative 2.82 squared. Well, what happens when you square a negative number? Okay, it's just a negative value times that same negative value. The negative sign is going to go away. So in terms of calculating the hypotenuse, this negative becomes completely irrelevant. Okay? Plus the adjacent, which is 6.03 squared. And what do we get? So let's figure this out. In my calculator, I've got 2.82 squared plus 6.03 squared equals. There's a number that's going to go underneath the square root. So while I'm looking at that number on my calculator, I'm just going to hit the square root button. Equals 6.66. 6.66. That 6.66 is the magnitude of the resultant vector right here. So the resultant vector equals 6.66 volts. Now all we have to do is find the direction. Okay? So again, like I said before, you want to minimize rounding error by using, given numbers if possible, or the numbers with the least amount of calculations. Well, we used both of these to calculate this number. So let's use both of these to calculate the angle as well. So do we use sine, cos, or tan when calculating the angle when we know the opposite and the adjacent? Well, the answer is tan. So let's see what happens. I'm going to erase this. We're going to try again. So the tan of the angle theta equals the opposite over the adjacent. What it is we're trying to calculate is the angle theta. Opposite over adjacent can stay right there. What do we do with tan when we bring it across the equal sign? We turn it into tan to the power of -1, or arctan. Okay? Equals, the opposite is, well, let's leave that number there for a second. Negative 2.82 over 6.03 all multiplied by arctan. First time I calculate this, I'm going to leave this negative sign out of it. Let's see what we get. 2.82 divided by 6.03 equals, second function tan equals, there it is, 25.06 equals 25.06. What? What did we just calculate? Degrees. Okay, let's try it with the negative sign. So it's negative 2.82 divided by 6.03 equals, now it's negative 0.4676 and so on. Second function tan equals negative 25.06. So what's the right answer? Okay, well, we know that the negative sign is right because we had it there. We needed to carry it on down. So that's the right answer. But why? Okay, here's where drawing it out is so beneficial. You could do the math without ever drawing any of this. Okay, but now you're left. And this one's pretty straightforward. Sometimes it's worse. Trust me. You'll discover this as you get into the work. Is you really do need to take a moment and stop and ask yourself, am I in the right place? Okay, so let's look at what we've got. Now I know that we're not really to scale here, okay, but is this working for us? 25 degrees. Is that right? I gotta be honest, it seems like a small number to me. I feel like it ought to be bigger. No, that's got to be it. It's this angle right here, negative 25 degrees. So this is 3. We slide it out to there. That was 70 degrees. Now that's Okay, I was anticipating that. It feels a little opposite over adjacent. No, okay, good. No, I feel a little uncomfortable about it, but the more I think about it, the more I'm convincing myself that that's the right number. Negative 25 degrees, right? Because we are down here in quadrant 4, okay, clockwise from our 0 degrees reference point, as opposed to the positive 25, which would bring us up here. Okay, so there you go. So that's the process. It is a lot of work, but it's really just a little bit of the trigonometry that you've already started into now with a little more purpose, rather than just trying to solve a right angle triangle. Okay, we're solving a right angle triangle so that we can translate back and forth between the two coordinate systems, so that we can add two vectors together, because we can't do that in the polar system. We have to take it to the Cartesian system. Okay, do the addition, and then take that resultant value and bring it back into a polar coordinate notation, because that's how we express our vectors. Okay, so that's the work for this week. The lab exercise sheet is going to cover sort of all of the math skills that I've covered through all of these videos, and it's all leading up to what comes next. Okay, I know I said this was going to be a heavy week. I know this is a lot of stuff. This is finally the end of it.